Right. Okay. Sorry, it was a bit late, but let's see. Board up. Wrong board. Right. Let's get started. Okay. So we just to quickly review what we did last time. Very quickly. So we were doing just a brief, very quick introduction to RL. And the idea is that, there is an agent in an environment. The agent is acting. It's observing the state of the environment and then taking actions based on that state. And it's getting rewards. And at every point of time, the network is, an agent is a network. It's outputting the probability of taking one of the actions. I mean, all the action, it takes the one with the highest probability, or it tosses a coin and then takes an action appropriately according to that probability distribution that it comes out at every step. And the goal is that to maximize the reward throughout the entire process or episode. In general, we try to take it as reward up to infinity, and therefore we have to put some factor called discount factor so that this whole thing doesn't go to infinity. And so we just write this down as and then we say this is the expected reward you want to maximize over all possible trajectories. You write it out like this. You perform this a bit of a trick that we discussed last time to get an expectation of the gradient of log of the probability distribution. And this log of the probability of a particular episode is just it's obviously the product of all the probabilities of every state action pair. And if you take the log, it's just the sum. And so when you write this out, it comes to something like this. Where is the error in this, what I've done? Please point it out. I told you there's an error in Slack. Is there an error? Can anyone point out the error?
In the second step, it should be summation of log of probability.
Absolutely. Thank you very much for being attentive. And this was just simply a writing error in the end of the class. So this is going to be log P of S I A I, right? And then we go ahead and compute this for an episode and you update and go on. Okay. We will, for the moment, we will skip the more complicated RL algorithms for now, but we'll come back to them just a little bit later. Okay. So this is called reinforce. Of course, the trouble with reinforce is that before making any update, you have to take an entire trajectory and then compute this loss. How do you compute this loss? By the way, this is still an error. Something wrong still. What is it? Something still I left out. Come on, point it out. Still not good enough. Tell me.
Probability value.
Huh?
Probability value. I don't
know. No. Just look at this equation. Look at this equation on top.
The gradient.
Gradient of log P of SI AI, right? So I hate those brackets, extra brackets. Okay, so let's just write it simply as gradient log P How do you compute this animal? Come on, guys. Those of you who've done neural networks. Oh, you've done neural networks, right? So how do you compute this? So there's a neural network which is given a state, it's producing a bunch of probabilities for each action, right? Typically, the neural network will essentially take your state and push it through a bunch of layers. Finally, there'll be a layer, right, which will then go in and produce a softmax, right? But you don't want. So there's also there is the instead of producing the softmax, you can produce the log of the softmax, right? So essentially, the log of this probability. So the probability is going to be the softmax. What you want is the log of the softmax, right? Correct? And so instead of the softmax, you actually end up producing the log softmax. This is also easy to compute. And I won't do the derivation here, but it's easy to do. But in PyTorch, you can, instead of writing softmax, you can write log softmax. And instead of taking the softmax of this guy, it'll produce the log softmax of this guy. You don't have to do it yourself because it's built in, it's a built-in function. And you can work it out. What is the softmax? And you can, it's the e to the whatever divided by sum, right? So the log of that is a simple calculation, but you don't have to actually do it explicitly. The PyTorch takes care of it. And then gradient of that is just the gradient of the log softmax. So you have an output of this neural network, right? Just take its gradient. And that's very easy to do because PyTorch lets you take the gradient. Sum that gradient up across everything that all the actions and states that you've seen. Multiply the whole sum. This, by the way, this is, yeah, so it's like this. We multiply it by the reward that you got at the end, and that's the gradient of your objective. And you're done. Clear? Okay. So now coming to MetaRL. So we talked about this last time briefly. Let's go into it a little bit more. So agent should be good at learning new tasks fast, right? So what is a new task? In RL, a new task could be a different distribution of states. For example, the states could be instead of images of in a video game, there could be sketches, there could be essentially slightly different, or it could be a totally different video game. And it could have different rewards. So in some sense, you could have each video game will have a different score and all that. So it would be a different set of rewards for maybe perhaps for the same video game, or it could be both of these. So it's basically a different environment, except that the state space, which is the X, right? Or the states which are coming out of, let's not call it X, let's call it S. The state space is the same. So S comes from the same space. It's like if the images, they're fixed, both the tasks have same size images and whatever. And the action space, typically written as A, the possible set of actions is the same. Then it's a valid different RL task for a meta learning algorithm. If any of these change, then I mean you're basically out of syllabus because the same neural network is not going to work on different state spaces, right? Of course, depends how you represent the state space, right? Okay. So it's last lecture, so let's just. I hope all of you have created a channel. Some of you have for your projects. So now we're going to apply MAML to this. So what do you do in MAML? The first thing that you do is what? Meta learning, right? So what is the first thing that you do in any meta learning algorithm?
Choose the task.
Sample RL task. And then you want to find out for every meta learning algorithm, you need to find out a D-train and a D-test, right? In the case of RL, what is D-train and D-test?
The state space.
No, training data. What do you train on over here?
The action space?
You train on data. What is the data you train on?
State action pair.
Yeah, so you train on a trajectory. You retrain a trajectory. Typically more than one trajectory, right? So you do this, and then you basically run the episode. So you get the tau, and then you what do? Well, you run an episode, and then in MAML, what do you do? Once you got some training data, this is your training data. You can run 1 or 2 episodes or whatever, but right now just run one episode. You get some training data, and what do you do? All the state action pairs are training data, and then what you do? Typically, you will do an adaptation, right?
Yeah.
Adapt model by gradient descent. Gradient what?
Gradient accent.
Descent. Right? On computed as above, and you'll get a theta prime. Then again, you'll run an episode. Right? This was my training data. This is now my test data. And you will compute the objective using theta prime. Essentially, you'll compute J of theta prime, right? And then you'll go out after doing all this, and you may run one or more of these guys. You can go and run a few more episodes in this case, right? Because in RL you typically will run a few episodes, not one, which is a bit, because you could do one, because if it's a long episode, you get a lot of training data, but typically you won't have enough, so you might run a few more. And then you will update theta plus alpha gradient with respect to theta. If it's just one episode, then fine. Otherwise, sum of all the episodes that you've actually run, and you'll go back here and you can sample another task, right? So typically, what you'll do is after every task, you'll end up updating this fellow. So you could have a sum over here, gradient of J of theta prime, right, across all these episodes that you're going, right, Ji. So you update the gradient, and then you can go back and sample more tasks, and you keep going, right? This is outer. This is your inner loop. Inner is just adaptation, and outer is updating the meta parameters, right, which is the theta, right? So this is simple MAML, but the problem is, for a lot of experiments have been done using MAML on reinforcement learning tasks, and it doesn't do nearly as well as on normal supervised learning tasks, right? And one of the reasons is that it typically in these tasks, rewards don't really come that often, right? So rewards in reinforcement learning tasks comes occasionally when you perform the task correctly or you win the game or whatever. Sometimes for those tasks where rewards come all the time, right? Like if you're balancing inverted pendulum or something like that, then this stuff might work well. But in tasks where the rewards are very sparse, they come sort of at the end when you win something or lose something. There's just not enough data for it to adapt without running too many episodes. And if you run too many episodes, then this particular gradient, second order gradient, has to back propagate through a lots and lots of gradients over here, and then you have this problem of loss of there'll be some vanishing gradient phenomena that happens. So this double differentiation doesn't normally work because you really have to then back propagate through many of these guys, and that becomes a problem. All right, so this is one case where the MAML is not really the best meta learning technique to use. So there's another technique which is some of you will implement, which is called RL squared. It's a model-based meta learning technique. And the idea is actually very simple. So let's look at a normal agent. What does it do? It starts in a state as 0. Based on that state, some agent computes some hidden state of its own neural network, and using that hidden state, it finds some action to perform. It moves to state 1. Some reward is achieved in state 1. State 1 then results, the neural network reads state 1 and produces a hidden state, takes action A2, and produces a reward R2. And so on and so on. It keeps going until finally it has some H n minus 1. It takes action an minus 1, produces state n, and finally gets reward n. Right. Oh, well, actually, sorry, this I got it wrong here. That's the key. This reward was because of this action, so this is R0. This reward was because of this action, this is R1. This is Rn minus 1. It also gets an Rn if it were to act in this state. It didn't act in this state, so it didn't get any reward over here. So you got n rewards, it ends up in state Sn, and let's assume that this is the done state. Now, how does the training happen? The gradient, which will sort of affect the weights of this neural network, which is going to produce this action, come because you are taking the log probabilities of these guys, right, and multiplying them by these rewards, and then taking the gradient, right? That's what this guy is, right, over here. Take the log probabilities multiplied by the reward, and then that's the and of course take the gradient, and then that's the gradient of the loss. So in this procedure, the agent can do nothing if there is no external fellow giving it, okay, now you've done this, let's take your log probabilities, multiply by the rewards, and take the gradient, and then I'll give you an update. So there's somebody outside doing this. Right? There's a learning algorithm outside, which is sitting around and figuring out that, yes, this is what's going on. Because the neural network itself doesn't take the rewards as input ever. Okay, so the rewards, Ri is never input to the agent or neural network. Is that clear? That's a very important observation. I mean, it's obvious, but it's an observation that just like in model-based meta learning, the key idea was that your labels for your training data had to be input to this model. So xi, yi would be input to the model. Whereas in normal machine learning, xi is there, yi comes out, and somebody else finds out how bad the yi's were, computes the loss, takes the gradient, and then updates the network, right? But in meta learning, you are actually, in model-based meta learning, we were passing in, if you remember, in model-based meta learning, we were passing in x0, y0, x1, y1. That's what you guys are all doing with your CNP, xn minus 1, yn minus 1. You're passing it into something. So it's getting labels for the training data also. The counterpart of labels here is the rewards. So the natural thing to do is, why not do the same thing that you say that you have your guy, your state is going to produce H0. You're going to get out an action A0. You're going to go to S1. You're going to get a reward R0. Yes. But you're also going to put that R0 in over here. So you not only take the state 1 to compute H1, you also remember that the last time, sorry, not just R0, you also have to sort of remember that you took action A0 and got reward R0. That also goes in. So the network gets the new state. It also gets what happened last time. Right. So if this network is able to remember, oh, last time was S0, because it already had the information of 0, it sort of kept it around in some way. And now it's got S1, of course, which tells it something about the new action to take. But it also realized that, you had an S0 and now you're getting A0, R0. So, well, was that good? Was that bad? All that was R0 a good reward or a bad reward? So the action that it takes next takes both of these things into account. So now you produce an S2, you get an R1 because it was the action in state 1. And similarly, this time again, you'll produce a, what would be here? A?
1 R1.
1 R1, right? And so on. And finally, in the end, you'll get Hn minus 1, which had as input A n minus 2, R n minus 2, coming from S n minus 1, and output is going to be on A n minus 1, producing Sn. Of course, this is R n minus 2, R. So it looks exactly the same, except that you're passing these rewards in along with the previous action. So the network now has enough information to learn about what rewards were actually coming. Now, if you look at this and look at this, this is exactly like reinforcement learning, except that what? The state now contains a little more. It contains this, just assume A0, R0 is part of the state. The previous action and the previous reward is part of my state. This is exactly what's going on over here. So if you just make the previous action and the previous reward is part of your state, this is exactly the same as reinforcement learning. There is absolutely no difference between this and this. And now what you do is you say, okay, well, the agent just continues to learn, right? So you're giving it, you just give this guy and you keep giving it tasks. You give it task 1, give it task 2, give it task 3. You just keep giving it tasks, and it's just like one big long episode that you'll have many episodes of task 1, you'll have many episodes of task 2, many episodes of task 3, and you're continuously updating your reward form, your total reward. Now, if the reward distribution changes in say task 4, reward distribution changes from what was here, well, it would have changed earlier as well between task 1 and task 2 and task 2 and task 3. So during training, this guy would have learned to say, oh, now it's a new set of rewards. I'd better behave differently. In similar states, it's getting, maybe it was winning in some state, now it's losing in that state. So now, that's the losing state and the other guy is the winning state. So I'll sort of adjust my actions to appropriately because it knows the rewards. And that's the basic, extremely simple idea over here in RL squared, right? Now, of course, this is reinforcement learning, but this is not going to be that easy to train using reinforce, because reinforce requires you to have a very long sequence. So essentially, in reinforce, you need a lot of you need the entire episode in order to actually get a gradient back into the objective, right? So what is done is one trains this using other reinforcement learning techniques, and we'll just quickly cover one very important one of those in a minute. One more important question is there. What is that? In normal reinforcement learning, when you end the episode, what happens to these states? When you start a new episode, what do you do? The weights have been updated, but you'll always start from the beginning of the episode. So the initial state, you'll initialize the neural network, not the weights, but the hidden state will start with something with an initial value, right? It doesn't matter here because the entire hidden state is being computed from this guy, right? But here, the hidden state over here would have been computed using. So if suppose you were to go on, and this is now a new task, right? So suppose you just started doing a new task over, give it a new color, right? We started doing the green task over here, or the red task, right? So this is now the first. This is the state suddenly changes. So it's now no longer the state. Suddenly you're now moving to this S0 of the red task, right? Well, you certainly can't give it AN-1 and RN-1. It doesn't make any sense to give it that over here. You have to basically initialize it, right? So this actually becomes an H0, and there is nothing that goes in over here, right? Because you're actually starting a new task, right? So you're giving it some information. So this reset of the hidden state happens every time a task changes, right? Now, there are papers which do that every time a task changes. There are papers which don't do it. They just ignore it and they just keep going, and they also work perfectly fine, right? So the team which is going to do this will have to experiment with both of these possibilities and see how it works, right? So any questions before going on to the more involved method for reinforcement learning, because it's best to cover that before ending. Is this clear? Okay, now we're going to cover just very quickly, in a very hand-waving way, we're going to cover actor critic, which is the most commonly used reinforcement learning technique algorithm. The key is that, so let's just go through the algorithm. So typically you will sample. This is normal reinforcement learning, not meta reinforcement learning. This is normal reinforcement learning. So you'll sample a trajectory, and then you'll update. So you'll instead of sampling a sorry, I made a mistake. You don't sample the trajectory. You sample. You're doing a trajectory, and in this you sample an action, right? Action. So you basically find from the network what is the probability of take an action based on the probability of this distribution of state action. This is your neural network, right? So you toss a coin based on this output and you get an action, right? You'll also get a reward. You observe reward. So you get two things, an R and an A. And now you need to update your policy, right? Because you want to update it more often than just waiting for the entire trajectory. So you'll try to do an update. So you'll try to do an update right here. Theta is theta plus alpha times the gradient with respect to theta of log P of S given A multiplied by R, right? But this R was for the entire trajectory. That's the problem, you see. The R that you had to multiply by was for the entire trajectory. But you only have one action here. So what do you do, right? So you really can't take this update. It seems that you can't take this update without seeing the whole trajectory, because you can't multiply by anything else here, because if you had the whole thing, then you're fine. And if you waited till then, you could do the update only after taking the whole trajectory. So those of you who know active credit, tell me what happens. Well, you say that, let me assume that there is another neural network, Q, which is an estimate for what the entire trajectory will give as a reward. Right? And let's assume that neural network is learning how to actually get an estimate for the entire trajectory. Let's for the moment assume this is true, then this is perfectly fine, right? If this neural network has already been trained, so one way to do it is, okay, you run this whole, keep the thing on many, many trajectories, don't do any updates, learn this neural network, and then start doing updates on this function which computes actions. That's one way of doing it, but that's not a very good way, because this neural network would have learned the trajectories based on random actions, whereas actually now you're taking different types of actions. So you still have to wait till the next round when you do this whole process again to retrain this neural network. So you want something a little better than having to do that waiting still, right? Are you guys getting me? This is a sort of very informal introduction to active credit. Okay. Well, any questions? Because I mean, those of you who don't know RL, this is, I think, the simplest way of explaining it, rather than going into Bellman equations and all that crazy things, right? Value functions and all that. It's just basically, gut feel that you have to update this guy sooner, but you can't update it sooner because you don't have the whole trajectory. Let's assume there's a neural network which gives me that trajectory's value, right? What is the reward for that entire trajectory? And then say, look, if that was this guy, then what would it be? Well, it's not exactly the reward for the entire trajectory. So this QSA is the reward, is an approximation for the reward for remaining steps if agent does A in state S. Now, if that is true, this is the big one, right? This is the big thing that you need to sort of understand. If it is true that this QSA is actually, so you got all, you done all this stuff as 0, as k, and now this q is saying that this q of s k given a, given any action, is an estimate for the balance, the entire sum of rewards I'm going to get after that, right? If that is the case, then it must also be the case that reward that you get at the step t plus the value that you would get at the next state. Say, let's not write it there, let's write it as t plus 1, a t plus 1, right? This should be what? What should this be?
RT plus 1.
No, RT is what you got in state t, which is what you got here. This is the this is by definition the guy which is the balance, right? Balance, but not balance from here, balance from. So what is the, by definition?
Qt comma q of st comma 8.
Yes. So if this is true, then this guy must be related to the next guy in this way, because this guy is just whatever I would get from t plus 1 onwards plus whatever I got right now, right? And so therefore what you do is I will train this neural network to minimize the difference between this and st comma a. And this neural network might have this neural network has parameters theta. This neural network might have parameters w, right? So, so this is what you do. You train these two neural networks in parallel, right? You take this step using QSA, you go over to the next step, and then you've learned this reward at time t. You're also going to take an action at the next time step, and then you update this neural network, right? So then you update this guy by so you do two updates. So you do two updates. You take this, and then you do two updates. You do theta equals, theta goes to what? This is already done, so we have to do one more update. Sorry. This is one update. One. And 2 is w goes to w plus some learning rate beta times what? Gradient of this guy, right? What is gradient of this guy? No, it's not mass, it's minus. It's not gradient ascent, right? So it is minus. It's gradient, you're trying to minimize this error, right? So minus gradient of this fellow, let's call it error. What is the gradient of this guy? Well, what is the gradient of this guy? Come on. It's just this guy, ET, times what? Well, what you do is you only take the gradient with respect to this neural network. You don't take both. I'll just come to that in a minute. So you just, so this will have a minus sign. So it'll be W plus ET times Q of gradient of, there'll be a 2 also, right? Somewhere, but that 2 will sort of go away in a minute. That 2 is absorbed in the beta in some sense. Beta times. So this will have a factor over here, beta, and this will be a E will come, right? This whole guy will come. And then this minus of this guy will come, right? Because, and this guy, you're basically going to gradient, you're going to update the guy at this time. And then there'll be another update for the guy at this time. And there'll be two of them. So this, but in some sense, you only do this, you forget about the gradient over here. You assume this guy is fixed, right? The next time step. So you only have to update one of them because that's all you care about. You're saying that this is what I had at this point of time, and I'm updating the network so that this value becomes closer to this value. And then you're done, right? So it'll in the next time step, this guy will get updated also, right? So everything will happen. So that's it. So this is the critic, and this is the actor. And it's a very, very loose, sort of non-formal introduction to actor critic. And there's just one more trick which is very important. Is this clear? Sort of. I mean, those of you who've done actor critic would see this very well. But those of you who haven't, just try to listen to the thing again and understand it, because it's very simple. It's all you're saying is that I'm assuming that I have this guy Q, and then I just train this guy Q so it actually does what I assume it to do. That's it. And then I can get rid of this updating only at the end of my episode. I don't have to wait for the other episode. I can keep updating every time. So it becomes much faster to train. One more trick, which is called advantage. And that's by a very simple observation that suppose the reward at time t is, say, reward of S of t, A t. And suppose you could take many different actions, right? Over here, right? Like suppose one action was 100, got a reward of 100, another one got 101, another one got 99, another one 102, and so on. So the 100 is sort of a very common thing, right? I mean, there's nothing very, why should you use 100? It'd be much nicer to use 0, 1, minus 1, 2, right? So that's cleaner. These things, numbers are so close apart, then they look so similar, the network will not get enough of a gradient to differentiate them. So basically you just subtract the value, the average value of all the awards that I have observed in state ST. So this is the expected value of the reward in ST for whatever action, right? So you just, here the average is, say, close to 100. So you just subtract that 100. And now you're only left with the difference. So it will not change the algorithm in any way, because all you're saying is the rewards are now being, you're just subtracting a constant value for every state, right? Because you only worry about how much better or worse one action is compared to the other. So this also speeds up the training a lot. So that's called AAC, Advantage Actor Critic, also sometimes called A2C. So that is a crash course in RL and an introduction to meta RL. Right. Now we're going to go on to a new topic, if that's okay. Cool. Topic. And it's probably an important topic because a lot of you have chosen projects in continual learning. Okay. So, okay, I can go on. Yeah. Okay. Continual learning is a situation where it's related, but not the same as something called online learning. Online learning is where old data cannot be seen. So it's like you don't have any memory. You don't have a storage, you don't have a hard disk. Data is coming, you're training your model and just keep learning something. But that data, you can't, you're not allowed to keep it. Right now, I'll explain the motivation for all this in a minute. I mean, that's perfectly fine. You can just keep learning and you can't see it. But all that means is that if there's enough data that, doesn't really matter if the new data keeps coming often enough, you don't care about the old data, because if there's enough data coming, then fine, you'll still learn, right? But if the distributions change, if the data changes the distribution, then performance on old data will suffer. Because clearly, if the neural network is not going to get retrained on that, you're just going to see some new data and forget about the old data. I mean, if that was a slightly different set of behaviors, then this neural network would have forgotten that. It's very clear. The weights will just get overwritten with whatever the new stuff is, right? Now, continual learning is similar to this, but the performance on old data matters. I'll explain the situation in the context of meta learning in a minute. So you don't want to forget. So you want to avoid. Right. Now, this whole motivation. So the motivation for all this really is not very practical, but there are some practical applications, right? So the motivation is more AI or modeling neuroscience type of motivation, which is called the plasticity and stability dilemma. So plasticity means that just because you learn to first you learned how to ride a bike and then you learned how to drive a car, doesn't mean you forgot how to ride a bike, right? But there are many aspects of riding a bike, like watching out for other vehicles on the road, navigating road, steering, braking, estimating the distance that you have to brake. All that skill does come in handy even when you learn to drive. So and you don't forget. So you don't want to forget. And the second thing is you also want to benefit some similar experiences. So the brain is actually able to do that very well, that just seems to have the capacity to keep learning new things and not really forget old skills, right? In a practical situation, there's actually less fundamental motivation for continual learning, except the following, that if there's a lot of data, old data, and you need to learn fast, the new data is coming fast, then for computational reasons, so if the old data is a lot, and you say you get some new data for the past 15 minutes, and you had 5 years data, and every 5-10 minutes, you can't keep updating your data model by rerunning through all the batches of the past 5 years every 5 minutes. It's just not feasible, doesn't make sense, right? So you need to be able to update your model rapidly without forgetting, And maybe when you have time at night or sometime in a batch job, you will update your whole model. But for the period of time where you haven't, you do want to update your old model, but not necessarily forget whatever things happened from the past, because those things could start coming even now, and then you wouldn't want to learn them from scratch because you've already learned them before, right? So then here's the concept of a task, right? Because it's not just data, it's actually a task, right? So more formally, it's not just old data, but old tasks, right? And or old tasks. So a task is a bunch of data, right? A bunch of data which has some integrity, it has a certain distribution, it has a certain set of labels, or in the case of RL, a certain set of reward distribution or goals, etc. Right. Now, there are a couple of different ways of, is it clear so far? Any questions? So for example, if you're an e-commerce site, let's take the example of e-commerce. You have data for all past data, and now you get some new data. And at this point of time, not only the new data, there are new users, there are new items. Suddenly new items have come on your shelf, not much behavior about them, but the old guy is also there. So if you just learned using just this data, you would forget about all the behavior that how people behave on other items, right? Which are already been selling, and you'll only use this a very spare amount of data. But you would like to do that in a manner so that you are doing it efficiently. That means you don't want to go and visit all the data, but you don't forget a lot of what you learned in the past, right? But then, of course, when you have the time, it makes sense to go back and train on all the data too, because that's more practical and you'll get better accuracy. But there may be cases where you don't. If the old data is just so old that the people's behavior is pre-pandemic and now it's post-pandemic, you don't care about the old data, in which case the CL issue just goes away. It's not, you don't care, you only want to adapt fast. Then it's a pure meta-learning problem. Right? So it's important to understand the practical aspects of it. So now there are a couple of types of continual learning. Task incremental, where there's a new task, which could be a new domain, a new distribution, or it could be what is called class. There are new classes or label distribution. So let me explain what these terms mean. So you have X's and Y's, right? You have the data and you have things. So these are my images and these are my labels, features, or labels, the dog, cat, animal, whatever. And then, you know, the domain is the distribution of your X, which comes from X. So the domain distribution is over here. This is sort of the concept. The concept distribution is the domain distribution. Concept distribution is the probability of Y given X or the probability of X given Y. So how do the labels and the images actually relate to each other? That's the concept distribution, right? What is the dog or what is a cat? Or suppose you had only you know, golden retrievers in your data set. Now suddenly you had all kinds of dogs. So the domain, so you're still talking about the same domain of images of dogs, but the distribution has changed, right? In terms of saying the number of dogs which are the kind of dogs for a given labeled dog is, earlier it was only golden retrievers, and now all kinds of dogs are there, right? So the dog cat differentiator would get a little bit more confused, because earlier it would have used features which are peculiar only to golden retrievers, whereas now you got all kinds of dogs in your dog cat classifier. Or suddenly, in this case, in the case of P of X, you had images, and now suddenly you have cartoons of dogs and cats. So you still have dogs and cats, but now instead of images, you got cartoons. So X itself has changed. Your domain itself has changed, right? Or you could also change P of Y. So now suddenly, earlier you had 90% dogs and 10% cats. Now you have 10% dogs and 90% cats. Or you have 50% dogs, 30% cats, and 20% something else, birds. So you could have new labels. You could actually have new classes. So that's called class incremental, where you can actually change the label distribution, or more popularly, the number of classes themselves, right? And you want to learn new classes without forgetting the old ones. So you're learning dogs and cats, and now you're learning dogs and cats and birds, now you're learning dogs and cats and birds and sheep, and now, but when you're doing all that, you don't want to forget the dogs and cats, because the dogs and cats you saw earlier, you didn't see them now, because now you're just seeing sheep and cows and whatever, and you don't want to forget dogs and cats, but you don't want to go and revisit all the data either. So that is the continual learning problem, right? Is that sort of clear? No questions makes me worried. Anybody?
Sir, how is concept distribution different from new classes or label distribution?
Oh, you might not. This is you could have this without a label distribution change, right? But this necessarily implies this.
Got it, sir.
You could do this without new classes, but this, with new classes, this will obviously change, right? But you could also have just the distribution of Y's change. So if you have new labels, certainly this will change, because there'll be new guys here. But you could have a distribution of labels change, like instead of 10% dogs and 90% cats, you have 10% cats and 90% dogs, right? Or rather, 10%. Sorry. The distribution of dogs and cats, earlier it was 90-10, now it is 50-50. But what a dog is and what a cat is has not changed. It's just that the balance has changed. So that could be also the case. Without new classes, right? So you could change this without changing this, provided there are no new classes. Yeah?
Yes, sir.
Okay. All right. So now we'll talk about one or two algorithms to do this. The key idea is this is an algorithm called Animal. It's not actually Animal. I'll give you the expansion of the algorithm in a minute. It's referred to as Animal. And the key idea is, what did we do in meta learning? In few short meta learning, what was the goal? Was to learn, was to do well on test data given small training set, right? And the solution was, well, if that's what you want to do, train for it. That means you created a training procedure where the network is trained in a manner that you will get some training data, some small amount of training data, and you will find how well you can do on test data by exploring that training data. Animal does the same thing. If goal is to avoid forgetting while also learning new things fast, this was the same as fast, right? Small amount of data. Well, then train for it. So same meta learning idea that we used in all the meta learning is used for continual learning in this animal algorithm. There are other continual learning algorithms which don't use this idea, but this one does. So it's derived from meta learning. So, well, what does it do? Well, you sample, not rather sample, it's rather you, that's to say, you get new task. Tasks are just sort of arriving and then adapt. So theta prime is some theta minus alpha gradient of loss on this task, right? Just like we did before. And then you sample. This was, of course, the gradient on the this was the loss was computed on the training data for the task, and then you what do? You evaluate loss. But now what is the loss you're going to evaluate? Loss using theta prime, obviously on the test data for this task, but also on some remembered set of past data. So what you do is for every task, you keep some data, not every task, for some tasks, you sample some data from some randomly sample and you keep it around. This is called sort of like a replay buffer. You don't keep all the data around. You don't go back and retrain on all the tasks, right? But you keep some of them around and just a small fraction of the data from the task at random you keep around. And the loss is computed on that small fraction as well. So this sort of avoids it to from forgetting. And then you say theta minus loss theta on gradient of, that's not alpha, whatever, sorry. It's exactly like MAML in that sense. Beta times loss theta. Let's just give it a name. Let's call this guy forgetting loss, LF, right? So LF. Loss which includes this forgetting bit. So you just do this, but then you don't do that again and again for many tasks. You just go back and get a new task. And you just keep updating, right? Now, so this process works for both class incremental, task incremental, and class incremental. But it's a tricky thing to see how it actually works for class incremental and task incremental, and the way the neural network is also very tricky. But let me just cover first the procedure of how this thing works, right? So you do this while training, and what do you do when testing? So the test protocol is kind of important to basically measure everything. So how do you test? Well, this is how you train and test. This is sort of the let's call it the protocol. So this is when you do meta training. Meta training, you have a whole bunch of tasks, right? T1, T2, TK, right? TM, let's say. And on this, you do this procedure, right? You sort of keep things around and you do all that, and you keep evaluate this loss and do all this stuff, right? And what have you done here? You trained it in a manner so that when it learns new tasks, it is trying its best to avoid forgetting, because if it forgot, then it would do badly on these guys, right? Now you come to the meta test time. And meta test time, there are two parts to it. There's meta test training and meta test testing. They are not data sets. These are actually parts of how you evaluate things. So for every meta test task, you will have a D-train and you'll have a D-test, right? So what you do is, so here what you're doing is you're adapting the thetas. So your theta is changing. So finally you started off with some theta, you get a, you're ready with, this is my theta finally, this is my, I'll call it my meta trained theta m, right? And here you're going to do a meta. But in this part, there'll be two phases. There'll be this meta test training. In that meta test training, you will keep doing this, right? So you're going to do this. You keep this T m plus 1 to T n, and you'll do adaptation. So what you'll do is you will take a little bit of the previous tasks, right, and keep their data around, but not all the data. So this data is split into two pieces, right? So there is a D-test training data, D-test sort of meta training data, and a D-test holdout. You'll see in a minute. So you only use this part. You use the training data and some of the testing data to do adaptation. So you're learning to learn with small amount of data. You're learning to not forget, but you keep these parameters fixed. You only make the theta primes, and you compute how best I can do, right? So I'm done all this over here. I have my theta from is actually this is my fixed theta. I've done all the meta learning for this. So the initial network is fixed from meta training, and I'm doing this sort of trick to avoid forgetting. And this network has been trained so that this trick works. Idea is this, so that this trick works. Every time you're starting from this theta, you're never updating it over here. But every time you do it, you take this data task and you evaluate this loss. So you're not ever taking the gradient. So all you're doing is you're evaluating this loss. This loss is never used on a gradient. It's just evaluation, right? So there's one. So you're going to get one loss meta test training loss, which is going to measure how well did I do on my test set, this part of my test set, and how well did I do it in terms of forgetting. It's just an evaluation metric. There's no nothing that you're doing. You're only adapting using this guy, right? So you're only adapting using the training data of the task. But since it's been trained not to forget, it would be such that this would not forget. That's the whole idea. So you'll keep evaluating how well is it doing in terms of forgetting. And this part, you'll evaluate something different. en plus 1, so say to t m n o p, or not say l m n l, right? So up to t n plus 1 all the way up to whatever, you will at this stage you will not only will you be not seeing so what you do, you say that at this stage you will be adapting using this this data, but you'll be testing on d-test. So what you're doing is you're saying, I'm actually testing on some data which I've never seen before. And I'll evaluate everything. I'll evaluate my meta testing, which will be this guy, which this guy will be the test data which is not ever seen before. So remember, you're going to do this, and you're going to evaluate all these losses after doing all of this. So all of these losses would be based on things which this guy would have been adapted using the previous task, right? So it would be adapting using this training task, and here you'll be testing using only new data. You would never have seen that data, so you will never adapt using it, right? So this is the protocol being used in testing, and what you observe in this protocol is that the network can learn and not forget. Now, I encourage you to read the paper in detail to see exactly how that works. But I think there are two important things that I need to cover before we close today. I think that will be all for today. One is that, see, this is important, because this part you're learning how well you don't forget. And this part you're learning how well you generalize to things which you've never seen before, right? Because you're generalizing here to stuff which you've never seen before, right? Because here you're adapting using this test data, right? Here, you're going to test using data which you've never seen before, right? So that's the key. Okay, so now let's go back. What was I going to say? Yeah, class incremental. In the paper, they test this on literally thousands of maybe 1,000 plus classes over here, and then this is 600 classes, right? So you're able to learn 600 every time a new class, right? And still not forget, and still generalize to on the test data of those classes. That's the key. Remember, class incremental learning means if there are 1,600 classes here, the neural network from the beginning will have 1,600 outputs. It's just that in the beginning, only one or two of them are going to get used, then 4 of them are going to get used, so on, and everything else will be always 0. And all those weights, all these weights down below in the beginning were over here, they'll all be 0 because they'll never get a gradient, right? Because you only see guys from this class. But the network is fixed, it'll always have this many outputs so that these hidden layers will be fixed, etc. So that's how you do class incremental learning. You need to know the total number of classes that you can ever support, and you keep adding them as new guys come along, right? That's one. You'll have to read the paper here. I will discuss it again next time. So if it's not clear. So those of you interested, please read and ask questions about this. But the very important part still remains in this paper. And that let me come to the name of this network. It's called neuromodulated meta learner. So neuromodulated is the key. So what is it that allows this guy to not forget? It's not magic. It's not only this procedure, because this procedure is not going to really help any network just remember things just like that without ever seeing the whole data again. Just a little bit of a sample of that data and only on this loss over here, right? So what this does is it basically has two networks. So there's a normal predictive network. It produces some guy and that goes out to a softmax. And this is your sort of softmax output. And there's a red network, which takes this same guy, produces this hidden layer of this size, and then there's an element-wise multiplication over here. So what that is doing is it's saying that whatever is produced over here is modulated by this, right? Now, what this does is it says, okay, it looks at this data and says, is it from which task? And based on that, it shuts off some of the stuff which is coming out of here, right? So effectively what's happening is, internally it's actually learning many different overlapping networks, some of which are going to contribute to this part, some of which are going to contribute to these classes, some of these classes. So when it sees a new guy, it gets an idea that, okay, this is from a task which includes these classes. So I should include some parts of this and not include some other parts of this. So it can do a better classification. So that's the way it ends up doing this learning, right? Or sort of learning to remember, right? Learning what parts to turn off and what to leave on. And this network is a large size. So this stuff is big enough. So whatever has been produced could be for older tasks. It says that which guy is it? So if it turns out to be an older task, it'll turn on the older pieces, right? And if it turns out to be a newer guy, it'll turn on the newer pieces in this list. And then that will go out towards the softmax, right? To the next layer, last few layers. This concept is actually a fundamental concept of modulation. And this, in some sense, it's all over the place. Attention also is a form of modulation. But there's a very recent paper called Hypertransformer, which does this kind of modulation, but actually modulates not this, but modulates the weights of the network. There's another paper that we're going to talk about next time called supermasks, which modulates the weights of the network. So the idea is that in a large network, in a very large network, very large network, there are many small networks, right? And some of them are totally independent of each other. Some of them are overlapping with each other, like this guy may overlap with this network here and this network here. So actually, if you have enough variety in your network, then the network can sort of mimic the sort of naive way of doing things of continual learning, as well, that you have network for task 1, network for task 2, network for task 3, network for task 4. And when a new task comes along, which task is it, right? If it turns out to be this task, then you go and pick up this network and then you use this guy. If it turns out to be the black guy, you pick up this network and use that guy. If it turns out to be the red guy, new guy, well, you choose some combination of these networks, right? So it's sort of saying, let's just keep a lot of networks around, right? But you don't explicitly do that. You make sure all of those networks are part of this whole big network. And this guy on the top is deciding which piece of the network to actually use. Hyper transformers do something similar. Supermass, which we'll cover next time, do something very similar as well. But the basic idea is that you will choose different parts of the network, right? And you're trying to mimic this naive way of behaving in a more sort of single network way, because some tasks may not require totally different networks. There may be a lot of similarity between this network and this network. So in that case, you'll leverage both pieces of the network when you do the modulation, right? So that's the idea here. Now there is one little piece which I need to go back and say, look, this guy has parameters. So the parameters of this network are in two pieces. Sorry, should be, there's a theta modulation over here, neuromodulation theta. And there's a theta here, which is the predictive network theta. And what this guy actually does is it, in the adaptation, it only adapts the, I suppose I should have written these in different colors. Let me just do that so that it becomes very clear. Let me get rid of this. Let's write it again. So that this part is red. And this part is blue. Neuromodulation. Then of course it's all black out there. Softmax. So the parameters of this guy are theta predictive. The parameters of the blue guy are theta neuromodulated, so modulation. And so actually then only these parameters are updated. Oh, sorry. In this part, only these parameters, the blue parameters are updated. And in this part, only the red parameters, which is the predictive network, is updated, right? Only this parameter is updated, the rest remains the same. So at the end of this training, the neural model network only contains essentially the M parameters, or the blue guys. They are fixed, and only the red guys get updated over here during adaptation, right? Only these guys get updated. The blue guys get fixed over here, and they get updated only during this training over here, right? So that's the fundamental difference between what I've got over here and the neural modulated network. Without this PNM, this was called, this is a paper called OML, Online Meta Learning, which essentially does this business of forgetting. The animal paper adds this neuromodulated thing, which actually tends to improve performance significantly. And this was the first paper where you could actually do continual class incremental learning on hundreds of tasks, hundreds of classes. You keep learning new and new classes, and the performance is not degrading too much. And you're learning the new class well, but the old class is also being remembered, right? Otherwise, getting new classes without seeing the old classes, you will sort of lose. Remember, the 1,000 classes that you saw here are gone. You only see new classes here, and the new classes over here, you haven't seen the remember, the adaptation never sees the old classes, right? So by the time you reached N, you wouldn't have seen these classes at all, right? For maybe 600 steps, okay? You wouldn't have seen any of those classes at all of training, and still the loss on all the old classes is evaluated. The loss that you evaluate is this whole loss, right? The whole guy over here. So you wouldn't have seen this guy yet. You trained on a lot of new things, but you're not sort of forgetting the old guy at all, right? You're still able to do well on it without adaptation. That's the key. Okay, that's what we had today. Couple of updates. Dates have been updated because of way the dates are, and because IIT ends the schedule a bit earlier, we will have 2 quizzes, not 3, and the dates are over there given. The project dates have been given. The IIT fellows students will have to give their projects a little earlier because their semester ends a bit earlier. But otherwise, the project end date is also given there for the other 2 institutes. And what else? I guess homework 3 is due next week. Homework 2 is due next week, and towards the end of next week, you'll get homework 3. Any questions?
Sir, about the homework too.
Yeah.
So actually, like, I mean, we had minor this week, like from Monday to today. So we didn't do the homework like much. So like if you could extend for like 2-3 days, it would be better because it was all minor this week. So
Which university?
IIT Delhi.
Right. Okay, so I'll talk to Mridul and he can extend it for a few days, just like we did it for extension for some people last week. So for IIT Delhi alone, we can extend it for a few days. We'll announce that on Slack. Okay.
Thank you, sir.
Anything else?
So I had a few questions about the implementation details for MAML.
Okay.
Okay, so first thing is that regarding the task. So, I mean, we can have like different classes, but is it also important that the number of classes are same for every task?
The number of classes that in MAML that you get is typically few short is the K short W ways, right? So if the network, see the maximum number of classes needs to be the same, right? Because the network has to produce that many outputs, right? If it's possible that in some task you don't get that many classes, the data is such, that's also fine. I mean, you could say this is a 5-way task, but you're only giving it 3 class data. That's possible.
Okay, so
but it would be suboptimal in terms of it's not the ideal, but in reality this will happen. But when you train things, you just don't worry about it.
Okay.
Training, you don't have to worry about it. Training, you just do it normally. There's nothing in the network which assumes that all classes have to be present. But while testing, you'll maybe get only 2 classes. How do you know? In testing, anything can happen, right?
Yeah. Okay. Fine. Okay. So
Of
thank
course,
you.
the training data, if the test class is not in the training class, it'll die, right? So in
Okay.
the
So I
task,
mean, yeah, this assumption is also there that the test class has to be there in some task during the training.
not some task. Sorry, the classes are agnostic. By the way, hello, classes don't. The class identity makes no. So in one task you could have dog, cat, bird as 0, 1, 2. In other classes you could have a lion, zebra, tiger as 0, 1, 2, and you could have dog also as 3. This 0 and this 3 have nothing to do in common.
Okay, so it doesn't matter if the classes that are present during the training time have to be present during the test time, right?
No, it's just a task. It's just a class.
Okay. Fine.
No, so that's the key. But if the classes in meta train, that's what I asked you to check. If the meta training classes and the meta testing classes, if this overlap is, if it's 100% overlap, there's a certain performance, and if there's 0 overlap, there's another performance, right?
Yeah.
That's what I need you to test.
Okay. So I was going through one paper that came after this MAML. So it basically studies the properties of MAML. It is called almost no inner loop.
Yeah, that's almost no inner loop is first. I think it's one of the one which only updates the
outermost loop.
the last guy, right? The head. So only this part of the network is sort of updated, the last softmax piece, right?
Yes, so
Yeah, that's just efficiency, right? In some sense, it's also doing it. You're updating only this part in the outer loop and only this part in the inner loop.
Yeah.
It's just more efficient, right? Because then you have to backpropagate through less guys in
Yes,
task
sir.
derivative, right? Yeah.
Yeah. Yeah. So I mean, that got me thinking if we can have arbitrary number of classes during the train set also. Oh, in the training tasks.
But your softmax have to remain the same. No?
Yeah. Okay. Thank you
Okay.
so much.
Okay. Right. See you guys. Bye.
Good night.